Alright folks, back here with another video where in this one we're going to be looking at, again, application of derivatives, where we're going to go a little bit further with that idea that the derivative is can be used to calculate an instantaneous rate of change in a function to a specific case, going a little further with it and looking at a specific case where we're going to focus our attention on looking at the instantaneous rate of change in position with respect to time, which is going to be instantaneous velocity in its calculation, and instantaneous rate of change in velocity with respect to time, which is an instantaneous rate of change description for acceleration. All right, we're going to be going into these specific descriptions, which involve looking at summarizing motion, right? Describing motion in space, right? And particularly here, a space that's one-dimensional. When we talk motion and we begin discussing motion in space and the concept of derivatives, you only have the concept of a derivative, particularly for a two-variable relationship where you have one independent value and one dependent value. If you want to move off into some two-dimensional space and move around, or if you want to move off into some three-dimensional space and move around, you're going to need a way of describing position with respect to time a little differently, right? And that's where the use of vectors is going to come in. At the current moment, we really don't have the use of vectors, so we're going to be stuck kind of looking at just the concept of motion along a linear path, right? Where we can move back and forth. Maybe just thinking about it as motion along a number line, moving back and forth or up and down a number line. We often consider these problems for projectile motion when we're thinking about tossing an object straight up against the force of gravity. That motion going up and then coming back down falls along a linear path if we throw something straight up against the force of gravity and consider it to be projectiling, right? Being the case for projectile motion. All right. So we're only going to be looking at moving along a line particularly, right? And here we begin with saying as an object moves along a linear path, the average change in position with respect to time becomes known as an average velocity for the object, and the average change in velocity with respect to time becomes known as average acceleration. And then furthermore, applying the concept of a limit to both of those descriptions, we're going to end up with instantaneous descriptions where we have the case for instantaneous velocity when we're looking at applying a limit to average velocity, or instantaneous acceleration when applying a limit to the average acceleration calculation. And when this is done, what we can define for a position function is not only the average velocity and average acceleration over some particular interval, we can actually calculate the instantaneous change in velocity and instantaneous change in acceleration, what are known as the instant velocity and instant acceleration for that description of position. Letting S equal to S of t describe position of a moving object along a linear path at time t, right? Instant velocity is the first derivative of that position function. If we take the first derivative of our position function, we end up with another function with respect to time, right? We obtain a function that describes velocity with respect to time. where at any given time t, we can use s of t to describe the object's position along that linear path. And we can use v of t to describe the object's velocity when it's at that particular position. As it moves along that path, it can move faster or slower along that path. Right? And at any point in time, as it moves back and forth along that path, with its description of position given by s of t, the derivative of s of t will describe its velocity at that point in time. It will describe the instantaneous rate of change in position with respect to time. Velocity, right? Velocity is the derivative of our position function. The instant velocity function is described by our derivative of our position function. Likewise, if we think about instant acceleration, it's actually described by the derivative of our velocity function. If I have a velocity function, I can calculate the average velocity over an interval of time, or I can use a limit and consider the instantaneous velocity at any given point in time as I move back and forth along this path. And if I consider the instantaneous change in velocity at any point in time, that's instant acceleration. That's the derivative of velocity, which we become known as the acceleration. And the derivative function for the velocity function is the acceleration function. And overall, you might consider the acceleration function then to be the second derivative of position. If velocity is the first derivative of position, then acceleration will be its second. With s equal to s of t, v equal to v of t, and a equal to a of t, these three functions, we primarily have a summary of any sort of functional description for an object moving along a linear path. And in fact, we only are going to find by the time we study calculus long enough, we only really are ever going to need one of these descriptions, along with maybe a few observations of the others, to be able to determine all of the descriptions, right, as functions of t. Some of that is going to come back in Calculus 2 when we're introduced a little further to application of the integral. Topic for Calc 2 students. Right? But at the moment, we're just focusing on that if we have a position function, we can take its derivative to find velocity, and we can take the velocity's derivative, which is the second derivative of position, and obtain a description of acceleration. Let's look at an example. Right? This is application of derivatives, folks. You can apply them in descriptions of motion along a line. Right? Oh, careful. Before I look at an example, I just set all this up using some very familiar calculations. You can see here we have those, instantaneous velocity calculations and instantaneous acceleration calculations, or instantaneous change in position for velocity and instantaneous change in velocity for acceleration, being set up here with their limits. Right, defining s prime of t and v prime of t as v of t and a of t respectively. But what's more of interest to us is actually maybe an example. So let's look at an example here. Let's assume we have this position function that's described by this parabola, this quadratic relationship, where the position at time t, we're moving along the line, and our position at time t on the number line is described by 60 plus 18t minus 5t squared. So if we're like at time 0, and we think about time being at time 0, if I substitute in 0 for t here, right, substituting in 0 in these other locations, everything will zero out except for the 60. That'll all turn into 0. And I'll be left with 60. I'll be at the location of 60 on the number line. If then I move to time t equal to 1 as time elapses over the first second, I will move along that line from 60 to or towards. And if I plug in 1 here, I'll get 18. And if I plug in 1 here, I'll get -5. And I'll position myself at 73 at that location. So from time 0 to time 1, maybe seconds, I moved from position 60 to position 73. I moved along the line over those locations between 60 and 73 over that 1 second in time. Right? I can think of that as being my description of motion with respect to time. Now I have to remember what function I had in there. Yeah, it was 18 minus 5t, because that's where we got the 73 from. It was 18 minus 5 is 13 plus 60 is 73. Right? Well, if I take the derivative of this function one time, it will give me my description of velocity. We can see that's quick calculation. Being polynomial, being a description of classical motion, which is polynomial motion, we end up with 18 minus 10t. Our description of velocity is given by 18 minus 10t. If we take our second derivative then, the derivative of 18 minus 10t is just -10. And we see that in this example. If we take those two derivatives, f of t, v of t, our description of velocity would just be the derivative of this function with respect to t, which is quick because it's polynomial. It's 18 minus 10t. And acceleration is described by the derivative of velocity. So 18 minus 10t's derivative is just -10. And collectively, these three functions summarize the motion of this object along a line. The position at any point in time t is given by this value, this function. Its velocity is described by this function, and its acceleration is described by this function. You'll notice the acceleration is 0. Well, sorry. The acceleration is -10. It's constant. This object is constantly accelerating. And I use that term loosely there. By accelerating, I do mean speeding up or slowing down. And this object is speeding up or slowing down at the same rate. And I have to be careful with that, because all that depends upon is also my velocity's interpretation. But I do note acceleration is constant. It's constantly -10. Velocity is linear. It's 18 minus 10t. And position, it's parabolic, quadratic. It's quadratic in its behavior. And again, if we go back to at t equal to 0, right, we note that we're going to be at 60 in position, and if I substitute in 0 here for t, I'd be moving at a velocity of 18 units. If it's feet, maybe it's 18 feet per second. If t was 0, my velocity would be 18 feet per second. My acceleration at time t equal to 0 would be -10 feet per second squared, because it's going to be constant. At 1, we know position is going to be 73 feet on our number line. The velocity will be 18 minus 10 times 1. It would be 18 minus 10, which is 8. We'd be moving at 8 feet per second. And again, my acceleration would still be -10 feet per second squared. All right? I would have these interpretations for my velocity, acceleration, and position. Right? Now, I did not put motion in here. Maybe I should add that. let's say here, describes the position of an object in a linear path. Oh, it does say measured in meters at time t equal to time t measured in seconds. So if we go down here to some labels, let's just add these in here. This is going to be measured in meters. This is going to be measured in meters per second. Right? Again, because it is, if we give a little bit of meaning to that, I guess I'll leave it as meters per second. Well, we can abbreviate. What am I thinking? We can say meters per second. And we can go up to this one and we can say meters. Again, some reasoning for that would be, again, this is just position, right? This is change in position, which would be change in S over change in time. Let me get it right there. Geez, can I get it right? So what is position measured in? Well, that's meters. And what is time measured in? That's seconds. So this becomes 18 minus 10t meters per second in its description. All right. That's where we get these descriptions of labels from. Right. As far as acceleration goes, you're measuring change in velocity, which is meters per second, with respect to change in time, again, which is another per second. Right. When you think about this, this is meters per second per second. So the way that that ends up being labeled out, if you think about just how fractions behave, this becomes meters per second, and you move those 2 seconds to the denominator, and a second times a second is a second squared. So we label this out as meters per second squared. That's how we'll sometimes say meters per second per second. It's a little cleaner way. So these would be our labels. All right. For these descriptions of our position, this quadratic function, our velocity, this linear function, and our acceleration, this constant function. Now, as for interpreting that motion, we might consider interpreting it over an interval of time from 0 to 5 seconds. To begin with, we might be interested in, when is the object motionless? Right? That object, if we note its position is behaving quadratically. And if we go down and look at a graph of it, here's the graph of that position. At 0, with respect to time, I should say. Here's time along the horizontal axis. At 0, we can see it's at 60. At 1, we saw that it moved up here to 73. The position was increasing. But it only increased to a point. At some point, it begins decreasing. Which means at some point in time, it went from increasing to decreasing. And if you just think about that, an object increasing to object decreasing, it had to reach a peak. And at that peak, it had to stop. You can almost imagine tossing a ball into the air. The ball will go up, getting slower and slower and slower, eventually stopping. For just a moment, it'll be motionless and then begin falling back to Earth. Similar idea here. There is a point in time where the object is motionless. And how do we figure that out? Well, that's when our velocity is equal to 0. Right? And if we look at our velocity function, it equals 0 right here. If we solve for that location, we do get 9/5 or 1.8 seconds, which matches into our graph exactly right here. And you can see the velocity starting here is at 18 meters per second, which is given by this location on the y-axis, right? When we substitute in 0 into this function for time, we get 18. But you can see the velocity is slowing down as that object becomes motionless at the time of 1.8 seconds. And then what happens is the velocity becomes negative because the object begins moving in the negative direction along the number line. Instead of heading out to 73, right, as it was heading, it's going to peak out right before 80 and then become dropping again, getting closer and heading back towards 0, heading towards the negative direction on the number line. So the velocity is going to be described with a negative value, and you see that down here. All the times greater than 1.8 seconds, our velocity is actually going to be negative. Right? Negative in terms of direction. Saying I'm heading back towards the negative direction. Before 1.8 seconds, it was still heading away from the origin, but then it stops and starts heading back towards the origin, towards the negative direction. It was slowing down before it was motionless, and then after it motionless, as it begins to head in the other direction, it's actually speeding up in the negative direction. That's where we see these larger and larger velocities in their absolute values. One of the things we should probably note here, and I should go back and do this. I can't believe I left this out here. Note, because this is crucial right at this point, the magnitude of velocity, which is the magnitude of our velocity function with respect to time, describes the speed of the object along the linear path. Right? We should add that in there. If we actually want to describe speed, that's given by the absolute value of the velocity. So even though these are negative velocities down here, they give negative values down below here, this close to negative 30 apparently, negative 40. Their absolute values indicate they're moving at 40 meters per second at those points in time. Right around between 3 and 4 seconds, we're moving at 20 meters per second back towards the origin. So what does that mean? Well, we would have had to slow down to become motionless, and then now we're speeding up. And how we see this behave, how we determine speeding up versus slowing down, is we actually compare the signs of the velocity and the acceleration functions. As we had noted, the acceleration is constantly negative, negative 10. The velocity is positive before 1.8 seconds, and it's negative after 1.8 seconds. So the object is motionless at 1.8 seconds. So when the velocity and acceleration are opposite in sign, when one's positive and one's negative, or one's negative and one's positive, the object is slowing down. When the velocity then becomes 0, we have motionless behavior. The object is motionless. We have no motion. And then when the acceleration and velocity become the same sign, as it moves in this case into the negative region and is negative along with the acceleration, when we're greater than 1.8 seconds is when the object is accelerating. We're actually speeding up, is how we would say that. They can both be negative and the object speeding up. The acceleration is back towards 0 and the velocity is back towards 0, and I'm pointing the wrong way on the screen. So the acceleration is back towards 0 and the velocity is back towards 0, and they're both working together to speed up the object. That's different than the other direction, where If velocity is heading this way, but acceleration is heading this way, they're working against each other to slow down the object. Right? Slow down the object until the point that your velocity becomes zero. Well, this would be your velocity case here. Would become zero and then would become negative and would head back with our acceleration as the object speeds back up. This is all described by classical polynomial motion. As we think about a polynomial, right, and it's describing a position function, its description of velocity and acceleration will also be polynomial. Always illustrating that slowing down to a stop and speeding up from a stop to a max speed. We can analyze these three functions and their, particularly the velocity and the acceleration signs, to start to determine when that object will be speeding up or slowing down. These are the three simplest cases for that situation. And in fact, what they describe very similarly is what we see happening in projectile motion, where all the acceleration is constant because that's due to the motion of gravity. All right? But this is just a quick little lesson on motion along a linear path here, folks. And when moving along a linear path, when we are given the position function, we can take its first derivative to find velocity, and we can take its second derivative to find acceleration. And or if we have the velocity function, we can take its first derivative to describe our acceleration. The acceleration function, what we call the instant acceleration and the instant velocity. Magnitude of velocity is always a description of speed. Velocity itself is actually a description of speed and direction. Being that it can be negative, it's describing heading in the negative direction towards negative infinity at a particular speed, which is given by the absolute value of that negative value. Right? And then when, in summary, describing the actual motion, if the two velocity and acceleration are moving in the same direction, the object is speeding up. And if they're moving in opposite directions, they're working against each other to slow the object down. All right. To the point where what will eventually happen in polynomial motion is you'll come to a point where your velocity is zero. And you'll be transitioning between slowing down and speeding up. Right? Because you have to slow down to reach zero and you have to speed up afterwards. Right? If you're just going to be stopping for one moment in time, like an object being tossed vertically into the air. Or even just a car moving up to a stop sign. Right? As you approach a stop sign, right, you have to slow down to approach the stop sign, stop, technically, right, and then speed up afterwards, right, to move through the stop sign. You know, if you don't behave in that manner, right, you're going to get a ticket. Right? If you don't stop, and if you don't speed up afterwards, any cop that might roll up behind you or watching what you're doing might become a little suspicious. So, and pull you over, right? Because you're supposed to move through a stop sign. That's classical polynomial motion. All right, folks? So, with that is more application of the derivative. That is still looking at, again, instantaneous rate of change, but looking at the specific cases for instantaneous rate of change involving motion along a linear path and change in position instantly being instant change in position describing instant velocity, and instant change in velocity describing acceleration. All right. More application of derivatives, folks. What we're going to come back to with the next one is we're going to talk about a topic of looking at derivatives as rates of change, but we're going to look at the topic of what we call related rates. And what that has to do with, folks, is every relationship that we have between variables, if those variables in that relationship were to change with respect to some other parameter, right? Those, as one of those variables would change, so would the other with respect to that parameter. And the rate of change in one of those variables with respect to that parameter changing could be described in the context of the other variable's rate of change with respect to that parameter changing. With respect to that parameter changing. And what we have are situations involving what we call related rates, where the rate of change in one variable in a relationship with respect to a parameter has a relationship with the rate of change in another variable in the same relationship with respect to some parameter. All stuff we have to develop, folks. So, with that said, we'll come back and look at that in our next video here. But all this, again, is looking at the concept of derivatives as being rates of change in a function. Here, it was the position and velocity functions, all right, giving us instant velocity and instant acceleration, respectively. All right, so see you in the next video, folks, and we'll continue this discussion.